In this lecture, we will discuss a linear transformation, which is rotation. Okay, what it tells, if we take a point on the x-axis, let's assume 1 0, and if we take a linear transformation, let's say t a b equal to a cos theta minus b sin theta, comma a sin theta minus b cos theta. Okay, if we take this, and if here theta is fixed, if you see in a linear transformation, this theta is a fixed. Okay, if we take another linear transformation, then theta will be changed. But in this linear transformation, okay, if we take a specific linear transformation which is rotation, then where theta is fixed. Then if theta equal to pi by 2, what does it mean? That any point, if we take any point on the x-axis, we get the image point on the y-axis, because we have a theta between x and y-axis is pi by 2. Okay, so any point it rotates by the angle theta. Okay, and we will show here that it is actually a linear transformation. Okay, it is a linear transformation, we will show at this time. Okay. Here T A B, okay, T is a map from R square to R square, and T A B is equal to A cos theta minus B sin theta, comma A sin theta minus B cos theta. Okay, so we will show it is a linear transformation. Linear transformation. How we will show that it is a linear transformation? Okay, so first we will show, take two element in R square, since this is a functions from R square to R square. Okay, we can see in the statement that t is a functions from R square to R square. Okay, so we have a functions from R square to R square, so we have to take 2 point in R square and assume x1 is a point in R square, means it will be of the form a1 comma b1, and a1 b1 will be real numbers. Also take x2 as a a2 comma b2. So we have a 2 point, and we will show that t of x1 plus x2 will be t of x1 plus t of x2. First we will show these terms, and then we will show t of alpha x. Alpha is any constant. T of alpha x is alpha t of x, where x will be in R square. Okay, then we will done. So here t of x1 plus x2 means a1 plus, what is x1 plus x2? It will be a1 plus a2 comma b1 plus b2, and t of this point. Okay, a1 x1 plus x2, a1 plus a2, and b1 plus b2. And now by definition of this function, which is first coordinate multiplied by cos theta minus second coordinate multiplied by sin theta. So we will do like this. Okay, so we have here this is a1 plus a2 cos theta minus b1 plus b2, this is a second coordinate, comma sin into sin theta. Okay, so we have a first coordinate which is image, and we will have a1 plus a2 sin theta plus b1 plus b2 cos theta. So we can see here definition that a1, okay, this will be plus, okay, this will be plus, okay. So this is a a1 plus a2 sin theta. A1 plus a2 was the first coordinate and sin theta plus b was the second coordinate, but here the second coordinate is b1 plus b2, that's why we have taken here b1 plus b2 cos theta. Now we can see here, we can write, we will prove this properties, okay, after proving this theorem. So here we can see, okay, a1 cos theta plus a2 cos theta minus b1 sin theta, okay, multiplying sin theta by b1 and b2, we will get this one, minus b2 sin theta, okay, comma, it will be a1 multiplying sin theta by a1 plus a2, it will be a1 sin theta plus a2 sin theta, and here plus b1 cos theta plus b2 cos theta. Now we can write here a1 cos theta minus b1 sin theta, okay. So this will be t of x1 plus x2 will be a1 cos theta minus b1 sin theta, okay, plus this term and this term, we can write a2 cos theta minus b2 sin theta, okay, comma, and the second coordinate will be, we can write like this, a1 sin theta plus b1 cos theta, okay, and this will be plus a2 this term and this term, we can write a2 sin theta plus b2 cos theta, okay. And by the addition property of a coordinate, we can separate this term, and, okay, and this term and this term. So it will be, we can write here a1 cos theta minus b1 sin theta, comma, a1 sin theta plus b1 cos theta, okay, and addition, we will add this coordinate by a2 cos theta minus b2 sin theta, we have separate this term and this term, okay, comma, a2 sin theta plus b2 cos theta, okay. And if we see, we got t of x1 because x1 was a1 comma b1, and this is nothing but t of x1, okay, and this is t of x2, it will be t of x2, okay. So please, if you have any queries, please ask in the comment box, okay, I will reply all the comments, okay. So you should be clear 100% and that how we have proved this theorem. Now we have to show t of lambda x1 equal to lambda t of x1, okay. We can so easily this, it will be t of lambda x1, we have a1 comma b1, and it will be t of lambda a1 comma lambda b1, and this will be lambda a1 cos theta minus lambda b1 sin theta, comma, and it will be lambda a1 sin theta plus lambda b1 cos theta, okay. Now we can take common lambda from this coordinate, and also this coordinate. So lambda will be out of the coordinate and it will be a1 cos theta minus b1 sin theta, and second coordinate will be a1 sin theta plus b1 cos theta. So we can see here that this term is nothing but t of x1. Okay, so we have proved that rotation is actually a linear transformation. Okay, now we will prove that kernel of this rotation linear transformation is null space, is zero vector only. Okay, the kernel of this linear transformation means the kernel of the rotation is a zero vector only. Okay, so it will be always a 1 1 linear transformation. Okay, so take any element, let AB belongs to R square such that T of AB will be 0. So we need to show what is need to show that A equal to 0 and B equal to 0 means the coordinate is 0. That's why the kernel, what is the kernel? Kernel is all the x in domain such that T of x is a 0. Okay, so we will solve for any x and we will show that x, if you take any x, will be 0 factor only. Okay, so we will show A equal to 0 and B equal to 0. So by the definition of this rotation map, it is T of AB is A cos theta minus B sin theta, comma A sin theta plus B cos theta. We can see here, this is the definition we have written here. Okay, so A cos theta minus B sin theta, A sin theta plus B cos theta. Okay, so we have here that, okay, so it will be 0. Okay, by the assumptions we have taken that T of AB is 0, and we will show that A comma B is a 0 vector in R square. So if it is 0 means 0 0, so first coordinate will be equal to first coordinate and second coordinate will be equal to second coordinate by the equality. So it will be A cos theta minus B sin theta is equal to 0, and here it will be A sin theta plus B cos theta equal to 0. Now separately we can solve this equation and we will get A cos theta equal to B sin theta, and if we solve this, cos theta will be in the RHS and B will be in the LHS, then it will be A by B equal to tan theta. Okay, so we can assume this equation as one and we will have here A sin theta equal to minus B cos theta if we take this term on the LHS, and it will be A by B equal to minus, okay, cot theta, and if we reverse it, it would be B by A equal to, yeah, minus B by equal to tan theta. Okay, we have reversed both the LHS and RHS. And okay, so this is equation 2. Now from equation 1 and 2, what we have seen from equation 1 and 2, we have seen that RHS of both the equation is same, so LHS should also be same. Okay, so it will be A by B equal to minus of B by A, and If we cross multiply, it will be a square plus b square equal to 0. Okay, and when two positive terms, this is greater than equal to 0, this is greater than equal to 0, and their addition is 0, it means individual term is 0. This is 0 and b square is also 0. It will be a equal to 0 and b equal to 0. So we have proved that the kernel of the rotation is only a 0 vector, means the rotation map is always 1 1 map. Okay. Okay, so thank you for watching this video. I will prove uh, another property in next video and give some example of the rotation map. Okay, so if you like, subscribe my channel. Okay, thank you.